Mr. Tarrou, in this lesson we are going to learn how to find the area of a surface of revolution. We're going to start this lesson off by doing an almost complete derivation of the rules that we'll need to find these answers to these questions. And then we're going to do one with a horizontal axis of rotation, a vertical axis of rotation, and our last example is going to be one where we need to rely on our calculator and to numerically work out the definite integral with our calculator, because it's going to be an example where we can't do it with our basic integration techniques that we know at this point. We haven't done any advanced integration techniques, though some of those problems didn't seem very basic. Okay, so to start this off, we are going to relate what we already know from our studies way back in geometry that we might have forgotten, and see how it helps us develop this rule that we're going to use in this video, this lesson. The surface area of a right circular cone. Well, I've got a right circular cone drawn. I have a circular base, of course, and it has got a height which is perpendicular to the radius of the base. And this value of L, which all of my textbooks have ever used, uses that letter to indicate the slant height, the distance between the vertex of the cone and the edge of the base. Well, when you look in a geometry book, it says the surface area of a right circular cone is equal to pi r squared, the area of that circular base, plus 1/2 2 pi r times L, or slant height. And when I'm in the geometry, the textbooks I've been using in the past years, when we do this concept, we have not yet done that much work with circles. So to explain the second half of this formula, the lateral area, which is what we're going to be focusing on the most in this video, the 1/2 2 pi r L, it kind of looks like the area of a triangle where it's 1/2 the length of the base times the height. And the slant height of the cone, when you take that lateral area and you open it up like a fan, and it is a sector of another larger circle, the slant height can be estimated by dropping an altitude down for, a number of triangle that you draw from the vertex of that sector. And, of course, actually this ties in exactly with the other part of this lesson, finding the length of a smooth curve, because, we're estimating the bases of these triangles become an estimation of the entire circumference of the circle, thus we get this 2 pi r. But then thankfully my Geometry 2 students don't start saying, well, that's not really the length of the entire circumference of the base, it's a little bit shorter, and that slant height that we're using as the height of the triangle is a little bit shorter than the actual slant height of the cone. But as we let the number of those triangles approach infinity, we are going to get an exact estimation of that lateral area. So if you're in geometry, which I know we're in calculus, but if you're in geometry and you want to explain how to find the area of this lateral area, you can also do it by explaining it with the formula for sector area. Because of course we do have an angle up here, right? And we have an arc length. So to find the area of a sector of a circle, you just simply find the area of the entire circle and then multiply by what percent of the circle are you talking about. And some formulas in your geometry book would say theta over 360, because we start in geometry using degrees, but we know in calculus and maybe your pre-calculus class, we much prefer radians. Now the reason why we like radians, by the way, and that will be pi r squared times pi over 2 pi, or theta over 2 pi, we prefer radians because really radians doesn't have a unit of measure. It's a ratio of two lengths. And if you're defining pi as the length of the radius of a circle and not the diameter, then we know that, let's see, we're at 0 radians, we're at pi over 2 radians, we're at pi, which is halfway around the circle, and then we're at 3 pi over 2, and of course 2 pi. Well, when you look at 180 degrees, which in radians is pi, that's how many radiuses that you would have to string end to end to get halfway around the circle. 3.14 radians, and of course it takes approximately 6.28 radiuses, their lengths, end to end to get all the way around a circle. So it's this ratio of two lengths. And so if you're doing an application problem that actually has units of measure, when you take it's within the same circle idea. So when you take these two values and put them over each other, the units of measure are going to cancel out. So that really makes a lot of our formulas in calculus much simpler. So everything we do is in radians. So when you see this pi r squared times theta over 2 pi, well, the 1/2 comes out front, the pi's cancel out, and we end up with 1/2 r squared theta. But now in my second line, I've taken r out, because I'm just pulling this formula out of a geometry book basically, and I'm specifically changing the value of r to L. The slant height of this sector area becomes the radius of this larger circle that we're looking at here, and of course we're looking at theta there. So we have a radius of this circle, and 2 pi r, again with this idea that radians is a ratio of circumference over another radius. 2 pi r is the distance around the base, the circular base of this right circular cone. Well, the length of this arc, now 2 pi r is a complete circumference of a circle, and I'm looking at this arc and I'm going, well, the length of this arc is 2 pi r, which is not, of course, all the way around this circle, but it is the entire distance around the circular base. So we are looking at arc length, 2 pi r, over L. Well, the arc length of the circle divided by the length of the radius. So that is, describing theta in terms of radians. And when you do that, again, radius of this larger circle, which is that sector area, and this green r, hopefully it's showing up in the camera as the radius of our base, well, then you have L squared divided by L, and the 1/2 times 2 divide out as well, and we have yet another sort of derivation, if you will, or explanation of how the lateral area of a right circular cone is equal to pi r L. Why am I making such a big deal about the lateral area of a right circular cone when we're supposed to be finding the area of a surface of revolution, which is all curved and smooth? And well, just like we estimated the length of a smooth curve with a bunch of straight segments, when you take these segments and you rotate them around an axis of rotation, you are going to get what is called a frustum, which is formed by cutting the tip of a cone perpendicular to the height, and you create two circular bases which are parallel to each other. Well, we are going to, and you'll see a better picture of it in the next screen, we're going to be having these straight line segments that are estimating the length of a curve, if you will, getting rotated around and creating a certain number of these frustum, and the surface area, the complete surface area of these frustum are going to estimate the area of the surface of revolution, and we're going to let the number of these frustum approach 0 as they become closer and closer together. Okay, so let's get on to the next screen where we start, showing how we're going to use this diagram to help us, because ultimately the next part of this is going to be, okay, well, if we understand how to find the lateral area of a complete cone, if we cut the top of it off, how do we find, well, the lateral area or the area of this frustum, so that we can then take a bunch of them and add them up together and find the total area of a surface of revolution. Now, in the rest of this video, this first scene is actually getting reshot. I misinterpreted the definition of a frustum. I labeled it as the entire lateral area of a cone, which is incorrect. So if I misspeak a couple of times, I'm going to try and make sure to put some text over the video so that's not confusing to you, and that's why I'm reshooting the first part of this video. So on to our next screen. Bam! So here we have our diagram. It's all cleaned up, and we are going to find just a portion of the lateral area of this cone. I want to slice the top off, okay? And what we want to do is just find the area, the lateral area of two cones, and simply subtract them. So we're going to find the lateral area of this large cone, which is going to be, let's see here, pi times the radius, which is going to be r sub 2, times the entire slant height, which is going to be L1 plus L2, L sub 1 plus L sub 2, and this is going to be the lateral area for the large cone. Now what I want to do is I want to subtract out the lateral area of the top cone that I've cut off. So we're just going to do subtract pi r times r sub 1 for another radius, of course, times this cone's slant height, which is L sub 1. Alright, so let's pause the video and get part of this cleaned up. All right, so we factored out, a common factor of pi. I took r sub 2 and distributed it through the binomial and got r sub 2 L sub 1 plus r sub 2 L sub 2 minus r sub 1 L sub 1. Now, I want to talk about this portion of the right circular cone, and I want to remove the references of L sub 1, this top slant height, and just have this section here going from the top of our portion of this frustrum to the base, L sub 2. Okay, because I want this top section to be gone. So at this point, there's nothing I can do with all of these expressions to somehow eliminate L sub 1 and have it all in terms of L sub 2. So what we have over here, we need to do something with the relation of all of these values and hopefully at some point get rid of that reference of L sub 1. Well, I've got a triangle here, which is a right triangle, of course, and we have some kind of angle up here, and then I have a large triangle, which is a larger triangle, which is also a right triangle that is also sharing this angle. So what we're looking at is the angle-angle postulate, which we learned again back in geometry to prove that two triangles were similar. So we do have a couple of similar triangles, which means that we can set up some equal ratios with corresponding sides. So we're going to say that we have r sub 1 over L sub 1. And that is equal to, let's see here, so that's the sort of base, if you will, of this right triangle and hypotenuse, and then we have the base of the large triangle, r sub 2, over its hypotenuse, which is L sub 1 plus L sub 2. So we're kind of going back to, again, proving two triangles and using with the AA postulate or theorem, and now using that to set up some equal ratios. We're going to cross multiply this, and we're going to get r sub 1 times L sub 1 plus L sub 2, and that is equal to r sub 2 times L sub 1. All right, distributing this r through here, we get r sub 1 L1 plus r sub 1 L2 is equal to r sub 2 L1. Okay, so now what? Well, if I group these two terms together that both have the reference to L sub 1, let's see what, actually, let's do this. How about, I'm still not going to be able to do one immediate substitution and get all the references of L sub 1 to disappear, but I've got L1 and L2 here with R, so in these two terms, and let's try and combine. Let's not try and get the L sub 1's together, but use this R sub 1, L sub 1, get that isolated, and we'll have a couple of terms with L2's and L1's and see what happens there. Just play around with it. So R sub 1, L sub 1 is equal to R sub 2, L sub 1 minus R1, L2. And now we're going to take this, we're going to plug it into here, we're going to distribute, we're going to combine some like terms, and just to speed things up again, let's just show that in some small steps. So after setting up that ratio from those similar triangles, we had that substitution, R1, L sub 1 came out. We had the R sub 2, L sub 1 minus R sub 1, L sub 2 go in its place. And thankfully, after we distributed the negative sign, we were able to cancel out the terms that referenced this top L sub 1 length or slant height, excuse me. And combining like terms, let's see here. Now we have two terms that both have an L sub 2, and so we factored that out, leaving us pi times L sub 2 times R sub 2 plus R sub 1. Now, of course, ultimately, we're trying to use this sort of, flat-sided frustrum, a lateral area of a right circular cone, to estimate a smooth curved surface of revolution. So, of course, we're gonna let this shrink to a width of approaching 0, giving us an infinite number of these frustums. And that means that, we're looking to, we don't need a separate R sub 1 and R sub 2 radius, we're going to work with the average of those two, very similar to when we were doing the finding volume with the shell method and talking about the radius of those shells, which is the distance away from the axis of rotation. So we're going to let we're just going to let this new value of r represent the average of r sub 1 and r sub 2. And again, as we shrink the length of this lateral area, the R1 and R2 values are going to become closer together anyway. So it kind of makes sense that we just want to use one variable of r. Doing that, we multiply both sides by 2 and we get 2r is equal to r sub 1 plus r sub 2. And that means that we can take this out, plug in 2 times r, and get 2 pi r times the slant height, if you will, only now the slant height is not going from the base of our cone all the way up to the top, but the distance between these two radiuses. Now this is the point where you're probably bored having me talk about all this anyway, but I'm going to skip the rest of this derivation because we just got done talking about, estimating the length of a smooth curve by a bunch of segments. And when we let the length of these segments approach 0, we saw through the derivation I did in the previous video how we're going to replace the value of L, this length, with the square root of 1 plus the derivative, or f prime of x, squared. So let's get to that screen and actually get these rules down so we can start using them finally in our 3 examples. Bye! And one more time, I know I'm repeating myself, but put it in words from the introduction of arc length, we know as we let the number of these frustum approach infinity, L, which is the length of the segment between these points, is going to be replaced with the square root of 1 plus f prime of x squared, if your function is y in terms of x. And if you want to see the part of this derivation that I'm skipping, you can watch my previous video in the my calculus playlist and actually, see that develop. Okay, and of course, as we let, again, the shrink to infinity, increasing the number of those frustum, just like the segments started to exactly estimate the length of that smooth curve, we're going to rotate that smooth curve around, creating a shell, basically, and we're going to find the surface area of that revolution. So the definition of surface of revolution, let y equal f of x, have a continuous derivative on the closed interval from, didn't put that up here, A to B. The area S of the surface of revolution formed by revolving the graph of f about the horizontal or vertical axis is S is equal to 2 pi times the definite integral from A to B of r of x times the square root of 1 plus f prime of x squared, forgot my bracket, dx. And that is the form you're going to use if your function describing this arc is a function of y in terms of x, and if the function that is describing this this arc segment, or just that segment that's creating the surface of revolution, if that's x in terms of y, then it's going to be s is equal to 2 pi times a definite integral from c to d of r of y times the square root of 1 plus g prime of y squared dy, and again that's when x is a function of y. R of x or r of y, that is going to be the radius, that is going to be the distance between the axis of rotation and your function. All right, let's finally, now that this has all been introduced, and I hope I didn't bore you too much, get to our first example. Set up and evaluate the definite integral for the area of the surface generated by revolving the curve y is equal to x to the 4th over 8 plus 1 over 4x squared on the closed interval from 1 to 2 about the x-axis. And the surface of revolution is going to look something like this. And then I got done with the last part of the video, and I'm like, well, why did I say I hope I didn't bore you? We just looked at what area, circumference of a circle, similar triangles, lateral area of a right circular cone, all these concepts that you learned in geometry still coming back, still being helpful, set up equal ratios and did a little cross multiplication and developed a rule that helped us to do something we've never done before. Find the surface area of some just curved surface of revolution. It's very cool, I think. So, okay, so we need to, it was S is equal to 2 pi times a definite integral from a to b of some kind of radius. This will be in terms of x because our function is y in terms of x, times the square root of 1 plus f prime of x squared. So we need to take the function and find the derivative. Well, that means that we're going to have, if y is equal to x to the 4th over 8 plus 1 over 4x squared, then y prime is going to be equal to, bring this 4 down, 4 over 8 is 1/2 x to the 3rd. And this is going to be, well, let's see here, that's 4 1/4 times x to the negative 2. So we're going to bring that negative 2 down. Negative 2 times 1/4 is negative 1/2. We're going to reduce that power by 1. So now it's going to be 1/2 times x to the negative 3, or it's going to be 1 over 2 x to the 3rd power. Okay, now remembering, like when we found the arc length, the length of a smooth arc or curve, we have to figure out this 1 plus f prime of x squared. So I'm now going to take my derivative and start, working it on the side into an expression that I can just plug right into the square root. So let's go ahead and find common denominators. We're going to multiply, we already have common denominators of 2, so we're going to have y prime is equal to, we need to multiply by x to the 3rd. So we're going to have x to the 6th minus 1 over, well, this denominator is only 2. That's why I had to multiply by x cubed, and we already have a 2. So it's going to be over 2x cubed. And now I need that 1 plus, so we're going to have now, working this in to a format that we need, 1 plus x to the 6th minus 1 over 2x cubed squared. Okay, now just to make sure this is all neat and speed this up a little bit, let's move off and reveal this one step at a time, and you can practice on your own. Took that binomial, squared it, got x squared minus 2x to the 6th plus 1 over 4x to the 6th. Finding common denominators, we have 4x to the 6th over 4x to the 6th, and combining like terms, we get x to the 12th plus 2x to the 6th plus 1 over 4x squared. Now, we're still, like I said, when we talked about arc length, we have only been using our basic integration skills. We haven't used any or learned any advanced techniques yet. So these need to be set up in such a way, unless you're going to have to use your calculator to finish the problem, to work out nicely. So this factors to a nice x squared plus 1 over 2x squared. Okay, so now now remember this one fraction squared is our 1 plus f prime of x squared. That means that that is going to go right there inside the square root. And you can see that the square around this entire fraction in the square root, that's going to handle very, very nicely. And we need an expression for the radius. So before I move our picture of our diagram away, of this surface of revolution we're trying to find the area of, the radius, well, the function is defining how far we are away from the axis of rotation. And we're looking for a vertical distance. So really technically it's like what? It's the greater y minus the smaller y. And since our axis of rotation is y equals 0, then it's basically the y that we're getting from the function that is defining the outside surface, which is, our x to the 4th over 8 plus 1 over 4x squared minus 0. And again, just in the context of this is all needs to work out very nicely with our integration techniques that we have to this point, I'm going to go ahead and find a common denominator here. We're going to multiply this second fraction by 2 and this first fraction by x to the second. And we're going to get x to the second, so we're going to have x to the sixth. This 4 needs to become an 8, so we need to multiply it by 2. And that's going to be x to the sixth plus 2 over 8x squared. And that is our single fraction that can describe the radius, the distance we are away from our axis of rotation. So let's get this out of the way, get it all cleaned up, and start revealing this process or the solution to this problem. Again, one step at a time, so you can try it on your own as well if you like. So of course, we let the power of 2 and the square root cancel each other out. We distribute the numerators and the denominators. Now I knew I was going to run out of room here, or I would have run out of room. So negative 1 plus 2 gives me positive 1x to the sixth. And then I separated, with only one term in the denominator, it's going to be easier to integrate if you give each of those, rewrite it so each of those terms in the numerator is over that denominator of 16 x to the fifth. So x to the 12th over x to the fifth gives you x to the 7th, and of course we have that 1 over 16. And that 1x to the 6th that we had after combining these like terms gives us a middle term of 1/16 x to the first, because the 6 on top cancels with 5 of those on the bottom when you pull it apart. And then we were left with negative 2 over 16 is negative 1/8, and that is going to be multiplied by x to the negative fifth. I don't like to integrate with my variable in the denominator, so I'm rewriting it with that negative exponent. Raise that exponent by 1 and then divide, and we get 1 over 128 x to the 8th, and so on and so on. I guess I don't really need to tell you now how to integrate a simple little monomial. And then expanding this expression, we have an answer. The surface area, or the area of our revolution, is equal to 150, 150, how about 1,053 pi over 256 square units. Now our next example is going to have a vertical axis of revolution. Pi! Set up and evaluate the definite integral for the area of the surface generated by revolving the curve y is equal to negative 1/2 x squared plus 8 on the closed interval from 0 to 4 about the y-axis. And when you do that, of course, we have a parabola opening down. The vertex is at 0, 8, and we're going to integrate or look at the curve from 0, the closed interval from 0 to 4. And we wrote that around, and this is what our surface of revolution is going to look like. Okay, and again we're revolving that about the y-axis. Well, we still need a y prime, and I can still leave, for these type of problems, I can still leave, even though we're going to be revolving it around, a vertical axis now instead of a horizontal one, I don't need to rewrite the equation in terms of y to match that different direction of axis of rotation. I can leave it, since it's already given y in terms of x, I can leave it that way. So I need an f prime of x squared, and then I'm going to add that with 1. So if this is my y, then y prime is going to be equal to negative, 1/2 times 2 is 1, so negative x. Let's see. That's rather simple. And now I need that squared. So, and I need it not only squared, but added with 1. So working this into an expression that we can, again, just straight away plug into our square root and save a little bit of space, we have 1 plus negative x squared, which is going to be, of course, 1 plus x squared. So now I have my expression that I can plug into my square root symbol there. This is my 1 plus f prime of x squared. Now I need an expression that describes the radius, how far this curve is away from my axis of rotation? Well, that's going to be the x that is defined by that curve minus the x that we have from the axis of rotation. And since my axis of rotation is the y-axis, that's x equals 0. So my radius is just simply x. Okay, well, this is quite a bit less work than our previous one. It's just a little bit of a slight, I got to think about it a little bit more because the axis of rotation is, the y-axis instead of the x-axis, but it seems to be going along quite nicely. And we're going to integrate, since everything is y in terms of x, we can integrate along the x-axis and integrate from 0 to 4. So let's get this out of the way. My fancy picture, old school style. And we have our surface of revolution, our area is going to be 2 pi times the definite integral from 0 to 4. My radius is just simply x times the square root of 1 plus x squared dx. So this looks like a pretty straightforward problem that we could do with u substitution like we did way at the beginning of our study of calculus, or we can do some pattern recognition. Inside this expression, which is being raised to the 1/2 power, right? Inside this expression, which is in the square root or within the 1/2 power, we have 1 plus x squared. Well, if this is, I'm not going to do a u substitution for this, we're going to do pattern recognition, but if we're going to let u equal 1 plus x squared, then du is going to be 2x dx. So I have an x and I've got a dx. If I introduce a 2 here, then I'm going to have that pattern of my u inside the radical or inside my power of 1/2 and then outside my du. Okay, well, let's just do that. Let's rewrite this as the definite integral from 0 to 4 of 2x times the square root of 1 plus x squared dx. But I can't just change the value of the expression. If I introduce a multiple of 2, I have to divide by 2. So then we have a 2 pi over divided by 2 out front, and of course those 2's are going to cancel out. And now when I integrate, with this being my, basically my u in here, and this is my u prime, I can just say pi. I'm actually doing the integration process now, so I'm going to take this, and it's being raised to a power of 1/2. I'm going to raise that by 1, so 1/2 plus 1 is 3/2. And then divide, how do you basically do the power rule of integration? You take the exponent, you raise it by 1, and then you divide by that. So dividing by 3 over 2 is the same as multiplying by 2/3 with my upper limit of 4 and my lower limit of 0. So let me just step out and finish up this little bit of arithmetic, and we'll get on to the next example. I took, to make life a little bit easier, our constant multiple of 2/3, moved it out front, then I went ahead and expanded this expression with our upper limit of 4 and our lower limit of 0, and got an approximate area of our surface of revolution of 144.708 square units. Last example. Bam! Same directions, of course, only this time our curve is y is equal to 2 natural log of x plus 3, and we're doing it on the closed interval of 1 to e squared. This is what our solid of revolution, our surface of revolution is going to, not a solid, a surface of revolution is going to look like when we again are rotating for this problem around the y-axis. Okay, well, let's find the derivative of y, or y prime, which is going to be y prime is equal to the, remember the derivative of natural log of x is 1 over x, so we have 2 over x. We're trying to fill in that formula. S is equal to 2 pi times a definite integral from a to b or c to d of some kind of radius times the square root of 1 plus f prime of x squared dx. So we got our y prime, and you get it squared and added with 1 again, so this is going to be 1 plus 2 over x squared, giving us 1 plus 4 over x squared, and finding a common denominator, of course, this is going to be x squared over x squared. So our expression that we're going to be able to put into that square root is going to be x squared plus 4 over x squared. Excellent. Okay, so now we have that 1 plus f prime of x. Again, our radius, our function is y in terms of x, so can I keep and calculate a radius that's going to be in terms of x? That's going to be the x of our, oh, I didn't highlight the portion of this curve which we're moving around. That's from 1 to e squared. And the x from our function minus the x from our axis of rotation is going to be, just x, right? X minus 0. So our radius is just going to be x again. Okay, so we know what a radius is. We know what the 1 plus f prime of x squared is. Get this out of the way. Again, one last time for our video, our lesson, and we get that s is equal to 2 pi from the definite integral from 1 to e squared. Again, our radius was just simply an x. The square root of 1 plus f prime of x squared is x squared plus 4 over x squared dx. You are not going to get, you're not going to be able to do a u substitution with this problem to get that to fit some kind of rule that we can finish this integration without the aid of a calculator. So, I mean, if you want the square root of x squared is x, so we get 2 pi times the definite integral from 1 to e squared of x over the absolute value of x times the square root of x squared plus 4 dx. And, technically the square root of x squared is absolute value of x. This is a little bit unnecessary because with our definite integration here, we're only going to be using positive values of x. And so when you look at that, you could say, well, then this is x divided by x, which is 1. So now we have 2 pi times the definite integral. And again, only because our lower and upper limits are positive are we not going to have to worry about keeping that absolute value in there. Now if you let u equal x squared plus 4, then du is going to be 2x, but there's no x out here. So we're going to finish this with the calculator. The integration, the numerical integration capabilities of our graphing calculators, and finish this last example. So you're not going to see me again, so I'm Mr. True. Bam! Well, finish watching the rest of this example, and then go do your homework. So, okay, we've got our calculator up here. We've got it on the scratch pad, and let's just go ahead and hit Menu, Calculus. We want to do an integral. The lower limit of that was 1, and the upper limit was equal to e squared, but I see I forgot to include the 2 pi out front, so let's do 2 pi, enter, times. Now, finishing that expression inside the integral, we had the square root of x squared plus 4 dx. And control enter to get an approximated answer, and that's 189.982 square units. If we had put the expression in like I had it with the denominator of x squared, that would have been, let's see here, how about 2 pi times, and this is another way you can get to it, hit this little button here, choose the, let's see, where did it go, right there, bam, enter, lower limit of 1, upper limit of, again, e squared of x, whoops, excuse me, get out of there, of x times the square root of a fraction, and that fraction was x squared plus 4 over x squared, again dx, and control enter, and we have the same 189.982 square units. So this is Mr. True. Thank you again for watching, and now go do your homework.